All right. Welcome. Welcome everybody. I wanted to I hope everybody's doing well. But I am I tell you recently I've been looking at for some reason I got into ampacity discussions with a few individuals, customers of mine, and it really caused me to ask some questions. Um, I know what we do, and I know for the most part why we do it. But when you take a look at what we're doing to apply, say, basic fundamentals like ampacity, if you take what you do and you say, look, where are the sections that support that activity? Where is the language in the code that supports what you're doing and what you're saying? It should be easy. In my opinion, it should be so easy, but it's not. And especially, hey, Nihad, especially in ampacity. And I'll tell you, Nihad, I'm struggling here with ampacity. So I decided that I am going, hey, sure thing, brother. I'm glad you got the invite. You gotta let me know. It's the first time I ever did that. So I thought I would take everybody through my journey through the topic of ampacity. So it's okay to say, hey, I'm having some brain blocks here because what I'm doing, where is the language in the code and how do they relate? And if you can't connect what you're doing with the code, you've got to determine, am I doing it the right way? Okay. So ampacity, I'm telling you, this is a very complicated topic. At least in my opinion, it is a very complicated topic. So I thought, hey, I'm working on a PowerPoint, and you know what? You know what, Nihad? So remember when you and I worked together live on our development of an IEEE paper? Okay, honestly, I think we could probably write an IEEE paper on mastering ampacity. We could probably write a book on this topic because it's not simple. And what I'm going to start with, and what I've done on some of the IEI News Live, I just did an IEI News Live session yesterday, and as I was going through that session, I thought, you know what, I really need to sharpen my pencil because there are some statements that I make, and and there are things that are being done that, no one is saying, hey, that's wrong, because that's the way we do it. But when I read the text, I can't find where what we do is being supported by the text. So honestly, I think this could be a really good topic for a live or a an IEEE paper that gets back to the fundamentals of mastering ampacity. And I am doing so here's my I have an opinion on this where I let me get this bigger. Man, cam A monitor right. Yep. All right, so this is my slide deck, and I am starting off with saying, in my humble opinion, we have conductor ampacity and we have circuit ampacity. Hey, Steve, I'm continuing this discussion from yesterday, and all of this started from a customer asking a basic question, and I gave him an answer, and I know the answer was right, but then I looked at what my answer was, and he's satisfied. He got what he needed. But then I'm looking at what I said, and I'm like, wait a second, where is that supported in the code? And I really couldn't find it. So I thought this goes back a little bit. So I started to do a deep dive on conductor ampacity, and I've come to this conclusion that I've got conductor ampacity and I have circuit ampacity, and they are two different things. Even if you look at the defined term of ampacity in the National Electrical Code, it says it's the maximum current that a conductor can carry continuously. It doesn't talk about equipment whatsoever. So when I use the term ampacity, It's no different, Niha, than when we talk about GFCIs. When I say GFCI, I'm talking about a Class A GFCI. I'm not talking about special purpose GFCI. I'm not talking about other ground fault protection of equipment. I'm talking about a Class A device when I use that term. So when I use the term ampacity, I am speaking to the maximum current that a conductor can carry continuously under the conditions of use. Now, we could argue and say part of the conditions of use for that conductor is the equipment that I'm terminating in. And the maximum current that that conductor can carry continuously is lowered. It's not because of the conductor, but it's because of what's at either end of that equipment. But, and I'm open to that. I'm open to that perspective. But I still liken it. I still say I have a conductor ampacity that conductor can handle based upon the conditions of use, which is temperature, because temperature impacts what the heating of the insulation and the number of current carrying conductors, because that adds temperature, right? So I don't have circulation. And if we look at 310.15 in the National Electrical Code, it's going to tell me I have to adjust and correct that ampacity value for those conditions of use. Once I land, if I have equipment that it places an additional restraint, I'm not doing that because the conductor can't carry it continuously, else it damages itself, exceeding its temperature rating, right? It says under conditions of use without exceeding its temperature rating. That doesn't speak to the equipment on either end. So in my opinion, I've got an conductor ampacity where I have the conditions of use that impact the conductor's damage of the insulation due to heat. And I have a circuit ampacity, which takes into the consideration the equipment and the terminations that are on either end. Yes, this is a special Wired Wednesday. I like it. Wired Wednesday. So, and Willie, I'm telling you, I'm struggling with I'm struggling with ampacity. And what I'm struggling with, I know, just like everybody, I've calculated ampacity. What I am struggling with is how what we do relates to what the words in the code. That's where I'm struggling. So I'm trying to do this tie between the language in the code and what we do and make sure they jive. And in that process, I even started to question some of the fundamentals that I know to be true, right? So it's like, wait a second. I'm looking at the language in the code and it doesn't say what I thought it said. So in any case, I'm going to walk through this journey, and this is probably going to be a multi-part series of just exploring this thing we call ampacity. And maybe we can all learn together. So anyhow, I'm saying, and there is no defined term circuit ampacity, but I'm suggesting that it's the maximum current that the circuit can carry continuously under the conditions of use, without exceeding, it says conductor and equipment temperature rating. So, I put that in. That's how good I am, right? So I added exceeding the conductor and equipment temperature rating. So I have to think about the conductor itself, which is the ampacity of the conductor. And then I have to think I can't exceed the rating of the equipment temperature wise, right? So if based upon the conductor size, I have a maximum amount of current that I could possibly draw over that conductor because of the temperature rating of the equipment, then I'm limited by that. Okay. I'm not going to exceed the conductor temperature rating because that value might be less than what the actual ampacity of the conductor is and what it can handle every day of the week and twice on Sunday. So I've got two aspects. I've got the equipment and the conductor. And in my opinion is that the conductor is the ampacity. When I think about the overall circuit, I think we need a new defined term for a circuit ampacity. And maybe we don't need a defined term. I think that we should be looking at it that way. Um, oh yes. So Willie, there's definitely some gray areas with the NEC. I know there are some arguments related to 110.14c1. And you know what, Willie, I haven't looked, and it was suggested to me by a good friend of mine to go look at the public inputs this last code cycle around 110.14c1. And And I haven't done that yet. I want to see where the arguments and debates are with regard. I know I made public inputs a while ago because I get frustrated in using table 310.16 for two functions. This was my biggest complaint or my biggest area of confusion when I graduated college. I worked under a PE, professional engineer at Gilbert Commonwealth out in Reading, Pennsylvania. And Mark Bryant and was my PE, and also Frank Angelini was another PE I worked under, and a few others. Jim Stembler, James Stembler. So in any case, I would do an ampacity calculation, and I would submit it, and the gentleman, whoever was reviewing it, would come back and say, "Well, no, you used the wrong column. You need to use a 75-degree C column." And I would go, "Wait a second. I have THHN conductor, and if I look at the 75-degree C column, THHN conductor is not there. So why would I use the 75-degree C column?" And they would just say, "Well, because you have to use 75-degree C because of the equipment." And that would be the end of it, and then I would just do it, right? So there's a problem with just blindly doing something, and in the hustle of bustle, especially in a consulting engineering firm, it's hard to find the time to say, "All right, I'm going to take you under my wing, and I'm going to teach you all those details," especially when maybe it's so freaking confusing that maybe that individual doesn't really understand it either. So, but in any case, that was my frustration, was using table 310.16 for two purposes. One was for the ampacity of the conductor, and the second one was for the ampacity of the equipment, the maximum current rating of the equipment. So, any case, I tried to make a public input to take that table and put it into 110.14. That died on the vine. It failed. And I tried it twice, and then finally I think I just gave up because I'm like, well, at least I know how to do it. But it is confusing. So in any case, I am going to say I believe we have a circuit ampacity which must take into consideration the amount of current, the maximum amount of current that the circuit can handle without exceeding the conductor and the equipment temperature rating. It's measured in amps. Okay, it's not a defined term in the NEC. This is the code by Tom. Okay, I'm gonna create my own code book here, but I'm gonna call it circuit ampacity. And Neha, this would, again, I think this would be a good IEEE paper. I'm thinking this would be a good IEEE paper. So anyway, so I'm saying here, I start out with simply, stating, and I put the little thinker in the background because I know this is probably going to be like, let me try to understand what you're saying. I have a conductor ampacity and I have a circuit ampacity, and they're two different things. That's out of the definition from the National Electrical Code. This is not defined in the National Electrical Code, but I'm making it up and sharing that with everybody here. All right. Now, I'm going to reference. So there are a bunch. I'm going to bounce around. So what I'm thinking is, and I'm not sure if I even want this slide or this. I don't even know if I want this slide because I think maybe in a separate document I could have some cliff notes to say, look, here are the different sections you're going to go to. Because I don't know. Anyway, just take that for what it is. I'm putting a hold on that slide just to say, do I do I want to walk through this entire presentation and then pull out the sections and then those are the related code sections? And should I even do that? I don't know if the value there. All right, so the first place I think that's why I think that's why it is so far up in Article 310. So remember, in Article 310, 310 is for conductors for general wiring. And you have the scope of 310, and you have 310.3, which is the conductors, and it says the minimum size of conductors. The minimum size of conductors for voltage ratings up to and including 2,000 volts shall be 14 copper or 12 aluminum or copper clad aluminum. And it says except as permitted elsewhere in this code. So really, I'm not sure. I'm not even sure the value of 310.3a in that regard, because you know what? This was a point of this. There was a certified amendment motion on this one. I think there was. I think I'd have to look in the 2026 code. I think there was a change to this. And he had in 310.3a, because I remember hearing the arguments on the floor about sending this one back to this language. But and the reason I say I'm not sure about the value of it, because it says except as permitted elsewhere in the code. So I guess I mean I can use a conductor smaller than a 14 and a 12. So the minimum size of conductors. So I'm not sure of what this one gets you. But in any case, I get the minimum size of conductors in 310.3a, and then B is conductor material, and it says conductors in the article shall be of copper, aluminum, or copper clad aluminum, unless otherwise specified. And it says aluminum and copper clad aluminum shall comply with the following. So aluminum and copper clad, solid aluminum conductors. So it gives you the material, stranded aluminum conductors. It tells you the insulation types that are permitted. And it tells you that copper clad aluminum conductor materials have to be listed. That's interesting. It's interesting that I guess a copper conductor is not required to be listed. Because if it was required to be listed, you wouldn't have to call out, if all conductors were required to be listed, you wouldn't call out copper clad aluminum. So, but in any case, you have the conductor materials. Doesn't have anything to do with ampacity. I'm thinking out loud. C is stranded conductors. Where installed in raceways, conductors 8 and larger shall be stranded, etc. And then D is insulated. Conductors not specifically permitted elsewhere in the code to be covered or bare shall be insulated. So unless it's permitted to be bare, then you have to have an insulated conductor. And remember, insulated conductors, the weakest link is the insulation. You don't want to melt the insulation. All right, so that's basically what 310.3, and then you go straight to 310.4. And 310.4 is critical for our discussion of ampacity because we have to understand the use. So if I look at this slide, I'm recognizing that in 310.4 we have to understand the conductor that I'm dealing with, and I would say we should even be looking at this when we select the conductor for the application, because 310.4 table 310.4 paren 1 gives us a lot of good information. And I gave you some, I basically put THHN in here and THHW just because THHN can be used in dry and damp locations. I can't use that in a wet location. I would have to use a THHW. And I believe on the IAEI's Tech Tuesday presentation that we did yesterday, somebody pointed out that a -2 is a 90° C wet location. So you'll notice, like in this THHW, this right here, this puppy is that puppy right there says 90° C, but it's a dry location. If you had a THHW-2, which doesn't exist, THHW, there's a THW-2. There's not a THHW, so there's a THW-2, which is a 90° C dry and wet location. So the -2 indicates that that 90 degrees, that wet location thing. But this is a very important thing, because, and here's where it's important from an ampacity perspective. You're going to get, whenever you do your adjustments and correction factors, you're going to do those adjustments and corrections based upon the temperature rating of the insulation. So if I'm using a THHN conductor, when I apply my correction factors and my adjustment factors for temperature and number of conductors in a raceway, I'm going to be using the 90° C column regardless, because that's the insulation rating of the conductor. Okay, so and it calls it out specifically in the code, even in 110.14. 110.14 says, just, and for your info, I'm using the 2023 edition of the code. So 110.14 says, it says that connection, 110.14c, conductors with temperature ratings higher than specified for terminations shall be permitted to be used for ampacity adjustment or correction, or both. So I can use the higher insulation rating for my adjustment and correction factors. In fact, let me see if it's in 310. I would look at 310.15. No, not 110.15. 310.15. Where is 310. Man, I screwed up. 310.15. 310.15 says 310.10. 310.15. Temperature correction and adjustment factors shall be permitted to be applied for the temperature rating of the conductor. And I have this because that sentence right there, there's one sentence in 310.15a that is, you have to stare at it to really understand it, and stare at it, and then when you think you understand it, come back and stare at it again, because it's confusing. But I'm going to go over that. So, but in any case, this table is important to know what is the insulation rating of the conductor, that whether it's a THHN, THHW, find it in this table, find out the maximum operating temperature for that conductor insulation, and then that will help you understand the column that you're going to use when you do your adjustment and correction factors. All right, so 310.4, table 310.41 is going to be an important table for you all. All right, so then 310.15, what's 310.14 first? 310.14 tells us, okay, 310.14, so let's do this. Let me show you something. Control C. I'm going to add a 310.14. 310.14. Remember, I told you this is going to be a working session. So 310.14 is ampacities for conductors rated 0 volts to 2000 volts. I'm going to take the dash. I want to get it all in one. There we go. 0 volts. I'm going to delete this, put a space there. I'm going to delete that space and put a space there. So I'm moving the spaces around. Rated 0 volts to 2000 volts. Okay, so it's cloudy and 78 degrees outside. So in 310.14, I've got a general, General, Control Z. All right, so what the general requirements tells me is I can determine the ampacities. We can determine ampacities based on the tables provided in 310.15, or we can engineer an ampacity, right? So that's basically what it's telling us. We can do the tables, or we can engineer it under engineering supervision. It also tells me where more than one ampacity applies for a given circuit length, the lowest value, always, and this is a theme, always use the weakest, always consider the weakest link. And I'm going to need an image for that. And there's an exception where different ampacities apply. So with an exception for small portions of the circuit. Okay, so if I have a very small portion of the circuit where that portion, based upon if I did the conditions of use, it has a lower ampacity, I can ignore it if it's small enough. And that basically is assuming that I can absorb the heat that's generated. So that's what A, and then what else does A tell me? A also tells us a general selection of ampacity, temperature limitations of conductors. No conductor can be used in such a manner that its operating temperature exceeds the insulation. So never exceed the temperature rating of the conductor. In no case shall conductors be associated together in such a way with respect to type of circuit, the wiring method employed, or the number of conductors that the limiting temperature of any conductor is exceeded. That would be your ambient. They give you an informational note. The ampacity tables, the principal determinants of operating temperature are as follows. Ambient temperature may vary along the conductor length. Heat generated internally in the conductor as a result of load current flow. The rate at which generated heat dissipates into the ambient medium. That's if you have insulation that covers it, etc. And then adjacent load-carrying conductors. Adjacent conductors have a dual effect of raising the ambient temperature. So you need separation. In fact, there is a thing for that. So that's in the general requirements. So then that's A. Then we have B, which is engineering supervision. This tells us that we can engineer, we can engineer a conductor ampacity. The equation is is provided. Basically, we're given the rope to hang ourselves. Right? So I'll take that out. So the equation for calculating the ampacity is there. We've got two temperature ratings, RDC, etc. So we're given that information in 310.14. All right. And then, so that's 310.14. We talked about 310.15. And so now we're into 310.16. So I'm going to delete that. 310.14, 310.15. All right, so 310.15. We didn't talk about 310.15, or did we? No, I don't think so. There's 310.14. There's 310.15. We establish the proper application of the tables that are included in 310.16 through 21. We can engineer an ampacity, temperature correction. That's A. B, you have your ambient temperature correction factors. C is your adjustment factors. That adjustment factors is the number of conductors. So let me go to B. What is B is ambient. That's your rooftop. You have your general requirements, ambient temperatures. You have your adjustment factors, which is more than 3 current carrying conductors in a raceway. And then you have a raceway spacing. And then D is bare or covered conductors, where bare or covered conductors are installed with insulated conductors. The temperature rating of the bare or covered conductor shall be equal to the lowest temperature rating of the insulated conductors for the purpose of determining ampacity. And then E is neutral conductor. This is your neutral conductor shall be considered current carrying in any of the following. So remember, okay, so this is an important one. E is where, whenever we are doing our adjustment factors for the number of current carrying conductors in a raceway, E tells us what is considered a current carrying conductor from a neutral perspective, because technically the neutral should not be carrying any current if you have a balanced system. So they give us 3 examples of when the neutral is considered a current carrying conductor. A neutral conductor that carries only the unbalanced current from other conductors of the same circuit shall not be required to be counted when applying the provisions. Okay, so if it's carrying the unbalanced, I don't count it as a current carrying conductor. The second one, in a 3-wire circuit consisting of 2-phase conductors and a neutral conductor, if a 4-wire 3-phase Y connected system, the neutral conductor carries approximately the same current as the line to neutral load currents of the other conductors and shall be counted when applying 310.15 Charlie 1. Important. And then on a 4-wire 3-phase Y circuit, where the major portion of the load consists of nonlinear loads, harmonic currents are present in the neutral conductor. The neutral conductor shall therefore be considered a current carrying conductor. So if I have harmonic loads, what are harmonic loads? Computers. I think you could probably, it would be hard not to count a neutral anymore, in my opinion. All right, so that's E. And then F is your grounding or bonding conductor. A grounding or bonding conductor shall not be counted when applying the provisions. So E and F have to deal with, they probably could combine both of those and title that section when and when not to, what would you call it? Current carrying conductors, right? What is considered a current carrying conductor? So grounding and bonding conductors are not counted as current carrying conductors. Remember, objectionable currents, Article 250. All right, so that's what those A through F is meaning. So then finally, and I don't know that I need to add more slides. I mean, I could put a paragraph for each of these and make each of these a separate slide. But I don't know if I have to. Now we're into the tables in 310.16. Now 310.16 basically introduces the tables. They got conductors are rated 0 to 2000. You got the 60 degree C, 30 degree C, and not more than 3 current carrying conductors. So the title of the table establishes the conditions of use for the conductors and the ampacity values shown. So remember, ampacity is always based upon a condition of use. It's not a rating, etc. And the conditions of use are clearly identified in the title of the table: ampacities of insulated conductors with not more than 3 current carrying conductors in a raceway, cable, or earth. The temperature, I should put I am going to do this for I am going to add insert picture from file. I'm going to go to desktop. I'm going to grab this screenshot. Okay. Ba-dum, ba-da. And I'm going to add another arrow shape. How about we do this? Control CV. And I'm going to do this. I'm going to have to angle it. Where's my angle? There we go. There it is. So, Willie Snyder, the grounding current only carries current on some HVAC equipment, and apparently, Willie, some appliances too. All right, so how you like my shirt, huh? Bobby Joe bought it for me. It's got, I don't know, it's got some leaves or something on it. I'm feeling festive today. So I have conditions of use. The other condition of use is in note 1, section 310.15b shall be referenced for ampacity correction factors where the ambient temperature is other than 86. So that tells me that these ampacity values are based upon 86 degrees Fahrenheit. And shall be referenced for more than 3 current carrying conductors. So it tells me I have no more than 3 current carrying conductors. And 310.16 has to be referenced for the conditions of use. So those notes are critical, and they help establish and support the fact that these current values are based upon conditions of use. And as long as I meet these conditions of use, the ampere values that are in this table, that conductor can handle that much current indefinitely, always passing through it. I won't damage the conductor. Okay? Steve, what is Steven saying? Steve is saying, in Article 100, there seems to be a separation of rated current of equipment and ampacity of a conductor. Oh, man, yeah, that's a good point. Rated current of equipment. Is that under R? LMNOP, rated current of rated output power, rated load current. I'm going to look under E for equipment. Equipment portable, equipment branch, equipment rack. Where do you see rated current of equipment? Hold on, let me do a search. Steve, help me out here, brother. Rated. This is not including the consideration of those items. Rated output power. Rated power. Rated. Where you see what? Steve, help me here. You said rated current of equipment. Rated current of equipment. I'm not sure where you see that. See definition overload and overcurrent. Ah, yes. All right. In any current in excess of the rated current of equipment or the ampacity of a conductor. Yes. Okay. Gotcha. Now I'm with you. And so what I would consider a rated current of equipment would be like if I have a panel board that can handle 100 amps, I can't exceed 100 amps. If I have a circuit breaker has a rated current, the rating, any current in excess of rated current of equipment. So circuit breaker, I guess I'd have to look at what the definition of an equipment is, but I think it's basically they're talking about the assemblies like like industrial control panel or something like that. But it's a valid point that you have a very valid point that they have this distinction between the rated current of equipment and the ampacity of a conductor. So which When we get to 110.14, we have to really ask ourselves, is it an ampacity value or is it a rating value? But suffice it to say, we're right here, we're on 310.16. This table establishes the conditions of use, etc., etc., etc. All right. Now, also, I have the temperature rating for the insulation. And what I'm going to do is I'm going to move this. I'm going to do this. And I'm going to do what I do, the voodoo that I do so well. All right, there we go. And I'm going to highlight that red, and I'm going to make it thicker. And then I'm going to do this and this and point down. All right, so those are the temperature ratings of the conductors. I have a 60, 75, and 90. That is just table 310. I'm sorry, yeah, table 310.16. If, crap, 310.16. 310.16, boom. There we go. So table 310.16, if I go to 310.17, I also have 60, 75, and 90. 310.18 is 150, 200, 250. So this is ampacities of insulated conductors with not more than 3 current, blah, blah, blahs. And this is in your same size, but this is different. This is your type Z, your FEPs, your PFAHs, TFEs, etc. So all of the tables in 310 that deal with the ampacity of conductor values are going to have a temperature rating for that conductor. All right. I already got that one. Both are considered, but as separate considerations. Yes, Steve. And I think that's why in my very beginning of this discussion, I'm saying we have to treat them separate. We treat the conductor ampacity, establish that, then we consider what is the maximum current for that size conductor that the equipment can handle. And I do those two things separately, and the weakest link wins. It makes sense to me, but I'm telling you, it's not that clear in the NEC. All right, so I got the insulation, and you know what I need? You know what I'm missing? Is it this? Yeah, I'm missing I like the little thing going on in the background. The little line thing at the bottom and all that. I had it hidden. I don't know why I had it hidden. Okay, so insulation temperature ratings are there at the top, so that tells me that information. Then I have my insulation types, and I'm going to do this. I'm going to do the same thing I did. Insulation types. I'll move that over here. And I'm going to I'm going to highlight this, basically give it a nice big red, put the weight in there, and I'm going to turn this on its end, shorten this puppy up, and move that right like that. Okay, so those are my insulation types. So this is where I'm going to give my THHN, my THHW. If I have my -2s for 90 degrees C in wet locations, all that jazz is going to be right in there. So those are my insulation types. And the critical piece of that, remember I said earlier, my 310.4 is going to tell me whether that's a 90 degree C insulation, etc. But I've already got that here. So I know in the 90 degree C column, I'm not going to have a conductor. But if I have a THH, put it this way, if I have a THHN in a wet location, I can't use that conductor. So I got to be careful about what's in there. I can't just blindly accept it. I have to make sure I pick the right conductor for the application, make sure the conditions, whether it's a wet location, dry location, direct bury, etc. I use 310.4 to pick that conductor, and then I'm using this puppy. All right? I'm liking it. I'm liking this. Okay, so that's what that does. And then I have my conductor materials, right? So it's copper, aluminum, or copper clad aluminum. I've got to use the right sets. So that's basically the layout of this table. All right. And then I have my conductor sizes. And then finally, those are my conductor ampacity values based upon the, not above, based upon the conditions of use. These conductors can carry the identified amount of current 24/7, 365, right? So, for example, a number 8 can handle, if it's a THHN applied properly, I can handle 55 amps all day. Give it to me, right? 55 amps. I'm not going to hurt the insulation. It's beautiful. It's poetry. All right, so, and if you can't tell, I probably had about 1,700 cups of coffee today. All right, so, all right. We're going to use this table. Unfortunately, we use this table for 2 functions. 1, to determine the conductor ampacity, and 2, to determine the circuit ampacity based upon the equipment temperature ratings. David Engelhardt in the house. Has it been mentioned that the -2 at the end of the location? Yes, we did. 90 degrees C wet. Thank you for that little awareness, Mr. Engelhardt. All right, so we did talk about that. That's all I have to say about that. All right, so 1, to determine the conductor ampacity, and the second time, now let me do this. And this is what I was going to do. Control C, V. Oops, Control Z. Control C, V. When we use this for determining, I'm going to get rid of this. White. Bam. In fact, oh man, yeah. Oh, no, you know what I'm going to do? Watch this. I'm going to take this, Control C, V. Watch this, David. You're going to love it. Picture format, crop. I'm going to bring this down like this. Boom. Then I'm going to do picture format, crop. And I'm going to bring this up like this. Boom. Boom, 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 boom. There it is. Look at that. Okay. When determining the equipment maximum current based on equipment temperature rating, this table, which does not include the insulation types, is used. Because this is what used to confuse me. Was, you like my shirt, Joe? Hey. Yep. So this table, what used to confuse me was they would say, well, you used a 75 degree C column. And I'd say, well, I got THHN conductor. And they would say, no, you got to ignore that insulation. Well, if I had a table like this, which, hold on. Let me show you something. If I go to UL67, look at UL67. Ooh, I should be able to do this. Bam. Here is the table 11.1 out of UL 67. Okay. This one says temperature rating of the conductor. And if you look, say a number one, a one gauge conductor. Let's look at 8. An 8 gauge conductor. 75 degrees C is copper is 50. If I look at this, 8 gauge, 75 degrees C, copper is 50 right there. I don't know if you're gonna. I think I gotta draw a little. I'll draw a little square. All right, so right there, there's my 50. Okay, so the two, these, what's in the standard for panel boards for terminating those conductors, I don't have, you'll notice, I don't have in here anything that says what the insulation rating is, because I don't care what the insulation rating is. When I'm dealing with the capability of the equipment, all I care about is the size of the conductor, because the conductor helps provide cooling, right? It helps heat sink. It takes heat out. So if I say I'm going to have a 75 degrees C, I can use a 90 degrees C conductor, and a number 8 at 90 degrees C is 55 amps. But if I have a number 8, copper, I can't pull 55. I can only pull 50. And what B tells me, B says, man, where is it at? B says, the ampacity of these sizes shall be the same for 60 degrees C wire when connected to a molded case circuit breaker, unless the breaker is marked 75 degrees C. And what we will do is mark our breakers 75 degrees C, so you can use the 75 degrees C value. Okay, so, but in any case, this gives you, in my opinion, if and this is what I tried to do twice, 2 cycles in a row. I sort of gave up, but I'm probably going to go back to there again. I think 110.14 should have a table like this, which excludes the insulation ratings, doesn't have you use the same table for 2 different things. This is the temperature rating, and I could get rid, well, I could leave the 90 degrees C column in there, because if I have a piece of equipment that's rated for 90 degrees C, then I can use that column. But for the most part, for breakers and panel boards and things like that, 75 degrees C column is what I'm going to use, and I'm going to limit. And what that would do is it could possibly make me increase the size of the conductor, which makes the conductor larger, which helps me wick the heat out of the assembly and off of the breaker. I love it. Or the fusible disconnect, right? So this table adds, in my opinion, some clarity. All right, so that's basically how I'm using these tables. I'm using this table for 2 things, and we'll get to 110.14 whenever we get there. Oh, we'll get there next. All right, so now, before I get to 110.14, did I cover, before I go there, before I go 3, did I do, I got 310.16. I'm good. So now, I have everything. I've covered everything I would need for a practical application to be able to do some adjustments for the conductor. Now I have to deal with the equipment. So I think I need to do, here's what I think I need to do in this slide deck. I'm going to add a new slide, and I'm going to call this equipment. I can't call it ampacity. Remember, I think Steve pointed out current rating. I'm just going to say equipment considerations. Okay, that's all I'm going to say. I'm going to say equipment considerations. And then up here, related code, I'm going to call this conductor ampacity. Oh, I know what I'll call this. Circuit ampacity. That's what I'll do it. That's what I'll call it. So the first part of this whole discussion is the conductor, and I'm gonna do add a section, and I'm gonna call this conductor ampacity. And then when I come down here, I'm gonna add a section, and I'm gonna call this circuit ampacity. All right. So, and if I go here, um, gosh, all right. Okay, so I have my conductor ampacity and then I have my circuit ampacity. And the circuit ampacity is when I'm going to be adding that dimension of the equipment. I love it. And then up here was this was my intro. And then these are my cases. So I'm going to do a control C. Case example 1. All right. Case example 1. And then this is going to be case example 2. Case example, because I think, in my opinion, the best way to understand and learn this is to run through examples. And I have 2 branch circuits, and I think maybe what we'll do as part of this process for mastering ampacity and creating this slide deck, which I'm going to eventually give. I'm going to walk through this, give this over to IEI, and have Paola make it look pretty, and not Paola, whomever down there. I'm not sure who the right people are anymore. I lose track. I can't. It's my own senility. I can't remember names and stuff. So, but in any case, I'll let IEI put this, wrap a bow around it, and then get it out to some subject matter experts to make sure that everything looks good, and then we'll make a program out of it. Okay, conductor ampacity. So we just did the conductor ampacity. 310.4, selecting the right conductor, do the applications, ampacities for conductors rated. We talked about all of this, adjustment factors, blah, 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 blah. Ampacity, blah, blah, blah. I could probably do an example. I could probably run an example here. Yeah, I am. I'm going to do that. I'm going to do this. Example conditions for conditions of use. Right? So I could take, for example, a boom. I could take a I don't know, a 1-aught conductor, copper conductor. We'll do it in the form of a question. What is the ampacity for a conductor for a 1-aught copper conductor in an ambient of 170 degrees Fahrenheit and with 6 current carrying conductors in a raceway? Question mark. So this is just like going to an IAEI meeting and saying, okay, what's that? What is the ampacity? So 1, ampacity based on 310.16 table. I'll just say table. Table 310.16 is, for a conductor with 90 degrees C insulation. Ha! Joe Bellatoni. I love it. I love it. 90 degrees C insulation. You and I thought about it at the same time. I love it. The ampacity is based on 310.16 is... There's 310. I'm in 310.18. 310.16 for a 1-odd conductor is 170 amps. 170 amps is 170 amps. We derating. I have to go to 310.15. Does not include the OCPD nor the connected equipment, but we all use the term circuit to refer to the OCPD. You know what, Steve? That's a good point. I'm gonna have to think about that one. I'm gonna think about that. That's a good point. 310.16. I go to 310.15b. All right, so I'm gonna say 310.15b. ambient temperature correction factor is, I said what, 170 degrees. Whoa, that's hot. Oh shoot, there it is. 107. I had to pick one that wasn't on the. I had so 90 0.41. Ooh, is 0.41 based on table 310.15b11. Okay. Then number of conductors in a raceway. And guys, follow along, please. Shoot them out if you disagree. I believe I'm using the right tables here. Adjustment factors. So 310.15c adjustment factor for more than 3 current carrying conductors in a raceway is, drum roll please, what do I got? I got 6. I gotta make sure I'm not gonna miss a meeting here. Oh, I'm good. 6. I got 6. 4 to 6 is 80%. Is 0.8. And I'll put 80%. Capiche? Thought I heard a text. Oh, yes. All right. Whoop, whoopa, whoopa. All right, 80%. So we've got the 6 current carrying conductors, and then we're going to do the math, right? So all right. Okay, let's do the math. Ampacity. So you know what we're going to do? We're going to do an insert equation. I'm going to bring it down here. I got to make this white. All right, type equation here. All right, so ampacity equals 170 amps times, go to equation, 170 amps times 0.4, is it 0.4? Yep, 0.41 times 0.8 equals So let's do the math. 170 times 0.41 times 0.8, 55.76. 55.76 amperes. Okay? So that's that. I'm going to copy this. And, uh-oh. Ah, there's that. Control Z, Control Z, Control Z. There it is. There we go. And I'm going to say that this conductor, without considering equipment, can carry 55.76 amps indefinitely without damaging the insulation, nor the conductor itself. Right? We agree with that statement? I think it's a fair statement. So that conductor, that's the takeaway. I adjusted the ampacity for this 1-aught conductor. This 1-aught copper conductor with 90 degrees C insulation, without considering equipment, because I haven't done that adjustment for 110.14, can carry 55.76 amps indefinitely without damaging the insulation nor the conductor itself. How do you spell indefinitely? There we go. I forgot a couple little letters. All right. So that, I got this wrong too, ampacity for a 1-aught conductor. Correction, there's 2 R's. Thank God for spell check, huh? All right, so we adjusted the ampacity from the table 310.16 based upon the conditions of use which we've identified. 90 degrees C insulation, 170 degrees 170 degree Fahrenheit environment, and 6 current carrying conductors in a raceway. That 1-aught conductor, which based upon the table and the conditions of use in that table can handle 170 amps, but based upon the conditions that I'm putting it in, it can only handle 55.76 amps. All right, so that I think rounds out the discussion for the conductor ampacity. I'm trying to think if I'm missing anything. I talked about the adjustment. Now it's not a roof. If it was a rooftop application and I was less than 3/4 of an inch away from the roof, I'd have to apply an additional factor. I don't have that, so I'm good. I'm good. And I have the number of current carrying conductors. So if you want to know what is a current carrying conductor or what's not considered a current carrying conductor, if you're dealing with like neutrals or equipment grounding conductors or things like that nature, you can go to what we already talked about. So that basically shows you how we adjust the conductor. And it points out the fact that I can handle 55.76 amps through this 1-aught conductor in that ambient and with that many numbers in a raceway indefinitely. I'm not going to heat it up to a point where I will damage the insulation of the conductor itself. I like that. Okay, so now I get into the circuit. Now, Steve says the circuit, by definition, does not include the OCPD circuit. Let's, by definition, what? Circuit. ABC. ABC. Circuit. What is the definition of a circuit? Circuit's not defined. Steve, where are you getting the definition of circuit from? Because I'm not seeing it being defined. I have circuit breaker, adjustable circuit breaker. I don't have the term circuit in Article 100 defined. And when there's no definition, make one. So circuit ampacity, and what I'm going to do, so help me understand what you mean there. Here's what I'm going to do is I'm going to grab this, Control C, and I'm going to put it right here, Control V. The maximum current, Control X. What if I put it here? Unformatted. Maximum current that a circuit can carry continuously under the conditions of these without exceeding. It's under class 1 and 2. Oh, it's under class 1 and 2. Oh, class 1 circuit. The portion of the wiring system between the load side of the class 1 power source. So class 2, that's class 2 circuit, class 3, class 4. I'm not sure I'm buying that one. Yeah, David, you're supposed to go to Webster's. Let's see, what does Webster say? All right, let's do that. Let's see what Webster says. Webster definition of circuit. Circuitry. A circuit, according to Webster's, can refer to a complete path around which an electric current flows. Regular route of a journey, particularly judges to preach electric. Okay, wait, hold on. Let's just go to circuit. Webster's definition. Oh, nope. Merriam-Webster's. Circuit, to travel completely around. Circumference is in a loop, and a tour is conference. Oh, man. Circuit. I want to. Related words, conference, syndicate, verb. Nevertheless, the studies now hundreds of players come. Damage to the. Oh, man. Try electrical circuit. Electric circuit. I don't know. I'm looking at class 1 as it applies to AC power. Well, I'm not using the term. Class 1 circuit, so I don't know. So you know what I'm doing is I'm going to define it as when I say circuit ampacity, I'm talking about the maximum current that a circuit can carry continuously under the conditions of use without exceeding the conductor and equipment temperature rating. So I'm going to define it for my purposes. He does have a point. I agree with you, David. Man. What if we call it? I'm just going to leave circuit ampacity. I'm going to define it here because I'm not saying a class 1 circuit. I'm defining circuit ampacity. It's just my term I'm using, and I'll have to think about a better term. If I can come up with a better term, then I will do that. But I want to include the equipment temperature rating. All right, so now we know Yeah, Steve, I see that. What Steve is saying, whoops, I shouldn't have put that in there. I hit the wrong button. The portion of the wiring system between the load side of the class 1 source and the connected equipment. Ooh, yeah. All right, so what we know, here's what I'm going to do is I'm going to say this. I'm going to put a new slide. I am going to say equipment. Now, what would you call this? It's not equipment limiting factor for ampacity. It's basically the limiting factor. It puts a limitation on the ampacity of, it can't be the conductor. It's got to be the entire circuit. I'll just say for ampacity. I can't say for ampacity. For the circuit ampacity. Because when I use the term ampacity by itself, it's a defined term and it deals with a conductor. The equipment is a equipment limiting factor for the circuit ampacity. We know that temperature impacts equipment and current carrying conductors generate heat. We know that. That's a fact. Oh. Hello, everyone. Thanks for joining. This week is second draft for the NEC 2026. Yeah, Nihad, that was a mistake. I hit the wrong button. Circuit ampacity. I like and its definition would be the combined considerations of the conductor. I like the term circuit ampacity, and its definition would be the combined considerations of the conductor ampacity and the equipment rating. Yeah, Steve, I think somehow I got to work that in. I like that. I like that as well. The temperature impacts the equipment, and the current carrying conductors generate heat. Whoops. For any given equipment, and specified size of conductor, a maximum amount of current for that conductor is specified. Right? So if I have a piece of equipment and I have a number, I don't know, a 1-odd conductor landing in that equipment, the equipment manufacturer, and based upon how it's tested, will tell me how much current I can pull, what's the maximum amount of current I can take on that conductor, because that conductor is going to generate heat. If I need more current over that conductor, then I'll have to increase the size of the conductor, which adds more mass. It also increases the amount of current I can pull over that conductor for when I land it on that termination. Hence, I'm not going to generate too much heat for the equipment, right? So the specified size of a conductor, a maximum amount of current, and that is going to be, and we use, I'm going to do this, we use table 310.16 and the appropriate temperature column to determine that maximum ampere value. Right? Makes sense? We know that for a fact. And this is the double dipping on table 310.16. And maybe here is where I'll give an example. Example table from UL 67 for panel boards. Bum, 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 and I'm going to insert picture from file. Boom. And what I can say here is, I'm going to put this like this. I'm going to insert a text box. Note. Ooh, I gotta give it a different color. Bullets. White. Okay. I'm gonna say, note the absence of insulation ratings, insulation types from this table. Note the correlation between the temperature, the ampere values for specified temperature for each conductor. Right? So when I say correlation, I'm saying they correlate with each other. They are equal. So when we went through, like, if I go 1/0 conductor and I go to the 75° C column, I'm going to see 150 amps for copper. I'm going to see 120 amps for aluminum. There's no copper clad aluminum. I like it. And also, I like it. And this shows you, oh, what does it say? I'm liking it. All right. What if we grabbed UL 489? Let's go to UL 489. I'm going to go to UL 489 now. 489 should also have temperature. Temperature. You got the cutest little temperature. I should also find the table in 489. I need to find the table in 489 for circuit breakers. 489 is the UL standard for thermomagnetic circuit breakers. There are 200. Oh, here we go. Not it. Jeez, oh man. Uh-oh. Not it. Oh man, come on, where is it? I'm at 173 out of 212. Yabba dabba 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 doo. Yabba dabba doo. I don't have the table. I don't see a table in here. Huh. 75 degrees C. That's not in there. What if I search for 1/0? Oh, here we go. Why didn't I see this? Terminal, current, and conductor size. There it is. Terminal and current in amperes. Size. Ah, chugga, 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 boom, boom. All right, so I'm going to do that. I'm going to do this too. All right, so I'm going to copy this, Control C, V, and oops, Control Z, Control C, V, and I'm going to say example table from UL 489 for circuit breakers. Okay, delete skis, Control Shift Alt 4, bloom, 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 and I'll do that's good enough. All right, so then we say insert picture from file. Where's picture from file? Pictures, picture from file. And I'm going to do this. R she blows, Cupcake Island. So there is the table. All right, so this is the example from 489. And let's do this. Note the absence of insulation types, because I don't care what the insulation is. I go by the size of conductors. This also includes the number of conductors. So if I look at 100 amps, tells me that for a 75 degrees C, I'm going to do this. There's my 100 amps. Note the absence of, note the correlation between the ampere values for the specified temperature for each conductor, right? So a 3 gauge, you go to chapter 3, a 3 gauge conductor at 75 degrees C should be 100 amps. 3 gauge, that's 100 amps. A 1, no, 60 degrees C, 60 degrees C, I can't go to a number 2. I can put a number 1 on 100 amp because that's 110 amps. So this goes by the size of the conductor. I'm going to say this table specifies the minimum conductor size for each terminal ampere rating. All right, so and then the maximum size and the maximum number will depend upon the manufacturer's and instructions. All right, so I gave 2 examples of how equipment will limit. Oh, and I'll say this, note that there is no 90 degrees C column in these tables. So I can't use 90 degrees C for a multi-case circuit breaker, for a UL 489 device. Ain't gonna happen because it's not even part of the standard. All right? Okay, save. I'm liking this. So let's go back through this. We got circuit ampacity. Temperature impacts equipment and current carrying conductors generate heat. For any given equipment and specified size of conductor, a maximum amount of current for that conductor is specified. We use table 310.16 and appropriate temperature column to determine that maximum ampere value. And we go, boom, table 67 gives us an example And boom, UL 489 gives us another example. What's Steve saying? Oh, I'm not even showing it. Crap. There we go. Oh, let me go back to me. Sorry. Hold on, Steve. Cam A, monitor right. There we go. Steve is saying, outside of the NEC, circuit is defined as a loop path. Yeah, I saw that. To include a source, a path to flow, and a load. Circuit ampacity could include considerations of all elements. I like it, Steve. I like it. Yeah, okay, I'm with you. I am with you, as it would include the entire loop and path of all things within. All right, perfect. So unfortunately, I had I'm going to take this out, the bullet. I have my thing, so I have circuit ampacity. I've got the temperature impacts the equipment. For any given equipment and specified size of a conductor, the maximum amount of current for that conductor is specified, and we use table 310.16 in the appropriate temperature column to determine that maximum ampere value. This is the example from UL 67 for panel boards, table 11.1. We have the size. I note the absence of insulation type. Oh, also note that 90 degrees C is not in this standard. Period. No period. No soap radio. So note that 90 degrees C is not in the standard. And then I give another example, UL 489 for circuit breakers. Note the absence of insulation types from the table. Note the correlation between the ampere values for the specified temperature for each conductor. This table specifies the minimum conductor size for each terminal ampere rating. And note there is no 90 degrees C column in these tables. Bada bing. All right, so basically what happens when I deal with equipment, the size of the conductor and the amount of current that I'm pulling through that conductor, that will generate heat. And I will test my equipment with a specific size conductor, meaning I can get larger, but I can't get smaller. And that conductor, I can only pull so much current over it. And I do that based upon either the 75 or 60 degrees C column, however the breaker or equipment, whatever that equipment is, however it is marked. I'm liking this. I'm liking this. I'm liking it. Okay, so my next step, now I'm in 110.4, so 110.14, I should do the parent text of 110.14. Well, so here's my issue with the parent text of 110.14. Joe Bellantoni. Is there a similar UL standard that shows ampacities for devices like receptacles? Oh, yeah. UL 498. UL 498. So if I go to UL 498, why do I know that number? I hope it's the right number. Yeah, 498 is receptacles. Jeez, oh man, God bless America. All right, so I'm going to go to 498. Okay, I'm going to maximize this puppy. Bump, 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 bump. I'm going to search for, I can't search for one odd. 14, I'll search for 14. 14 AWG. Receptacle employing combination and limited to terminals shall comply with the applicable performance. Boom. Boom. boom, boom, boom. I'm looking to see if there's a table in here. Is that Steve? No, Joe. Hmm. I'm not seeing a table. Um, Now we have specific conductor sizes. 6 devices are 14 copper. We specify conductor sizes like 14 and 12. Let me look at temperature. Let me search for temperature. Temperature. We got a pull-out test. We got a push-in terminals. Temperature test. A push-in screwless terminal for a factory device was tested. For a factory device, for a factory wired device, the size and type of conductors. The assembly is described in blah blah blah. The test described in this section may be conducted in conjunction with conductor insertion and reinsertion. There's a conductor push-in test. I'm not seeing it for a. Oh, here's the. Each terminal assembly is to be conditioned by inserting and releasing a solid 14 gauge conductor of the type to be used. See, they're specifying the actual size of the conductor. They tell you where to put the thermocouples. I don't have that same. They tell you the size of probes. I'm not seeing it there. Not seeing anything in the standard. I'm not sure why. Temperature tests. Unless in here they're referencing something else. They could be referencing an external document, but I'm seeing a lot of, I'm not finding a table. And I'm just, hold on. Those are horsepower ratings. NEMA configuration, and then there's the horsepower rating. So I know one of the factors that are important for receptacles is the size of the conductor. Can it wrap around and deform? So I know there's requirements in here for that. And then you mark it accordingly. But I'm not seeing, and I know that receptacles all have what's the temperature rating of a receptacle? Temperatures of a receptacle is not 75 degrees C. There's a temperature rating. I think it's 60. Is it 60? Sure, boy. This is a good question. Anyway, well, Joe, I'm going to have to think about that one. All right, so if we go back to this, Control Z. I got my circuit ampacity. I got my temperature impacts the equipment. There's examples from 2 different standards. Then we get into 110.14 and what I was thinking of. So in the parent text of 110.14, so the parent text of 110.14 says, because of different characteristics of dissimilar metals, devices such as pressure terminal or pressure splicing connectors and soldering lugs shall be identified for the material of the conductor. that should be somewhere down below. I would expect that 110.14 parent text would say something like landing conductors on equipment will impact the performance of that equipment from a temperature perspective, and heat can be generated from the termination, from splicing, it's blah, 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 blah. But it goes straight into dissimilar metals, which should be covered somewhere else. There should be dissimilar metals. There should be 110.14a, dissimilar metals. Anyway, conductors of dissimilar metals shall not be intermixed. There's just too much in that parent text. And then it says connectors and terminals for conductors more finely stranded than Class B. So there's a fine stranded. So they got so much in the parent text. Those are requirements that should be in first level subdivisions. That's the first change I would make to 110. 110.14 needs some work. So 110.14 parent text doesn't mean a hill of beans when it comes to ampacity calculations. Not at all. Talks about dissimilar metals, talks about finely stranded, talks about fluxes and solders. Terminals, connections of conductors to terminal parts. So what we're gonna, here's what I'm gonna do is I just got a note, I gotta join in on another call. So what I'm gonna do is I'm gonna stop this here. This is our journey. Our journey will begin. We've gone on for a little over 2 hours, or over an hour. I think I started at 12:30, 1:30, an hour and a half. So it's good enough for today. We had a great discussion. I appreciate everybody joining in on our debates and discussions. So I'm going to have to run because work is calling and I got to join in on the discussion. So, any case, thanks guys, and I'll set up another time for us to go through this again. And I'm going to say yes, I am available. All right. Thank you for joining in. Thanks for what you do for electrical safety and all that jazz. Thanks, Nihad. Thanks, Joe Bellatoni, Steve, etc. All you guys and gals out there. We will catch you. I'll schedule another time. Same bat channel, same bat time. Do the same thing. And we'll continue our discussion. We're going to dig deeper into 110.14 now because we've got conductor ampacity going through. So thanks, Joe. I really appreciate your input. All right. And maybe we can get some public inputs for next cycle out of this. And Nihad, we're going to get an IEEE paper as well. All right. Take care, stay safe, and God bless.